Section 11.3, the Kruskal Wallis test. So this is our first non-parametric test that we can actually use our guru for, which is exciting that we can do that. But I hope you guys have seen that even the non-parametric tests that we could not use a software for, there's a reason. I mean, they're so basic that I don't see why a software couldn't do the sign test because it is literally subtractions and additions of negatives and positives. But it just hasn't been done yet. And maybe because it's so simple, they don't see the point in making a software do that test for them. I'm not 100% sure. Okay, let's head over to our PowerPoint. Actually, I'm going to bring us to Blackboard real quick just to make sure you know where everything is for this week. I didn't do this in 11.2 video. I probably should have. But when we are in our weekly content folder, you'll see that after the Pearson PowerPoints with all the solutions in them and these videos that are very helpful, there's the case study that's due this week, and then you have all my lecture stuff tacked on to the bottom. So these are the lecture PowerPoints that I have used. The data sets that I used are all in here. That table I referred to in the 11.2 video, this is the picture of the table. And then my recordings are in this WebEx link where they've always been. It was called WebEx before. I just changed the name this week to WebEx Recording in case somebody did not find them. They are here. So even though I'm not live, I'm still posting my videos every week for every section under your folder. And you have all of those here on the bottom. So the 11.2 is already posted, and very shortly, once this video becomes available to me, because after I'm done recording, it does take a while. Now that everybody's using WebEx, it will be posted some point today. Okay, let's go to our PowerPoint. Here we go. Okay, so the Kruskal Wallis test is another non-parametric test. The assumptions are the same as the former non-parametric test. The random samples need to be random. Okay, for the Kruskal Wallis, the random sample is taken from each of k possibly different populations. So it's saying that there is no limit to how many populations you can use for this test. And the data also has to be such that it can be ranked, so ordinal or higher, so no nominal data. The procedure is that the hypothesis, the null hypothesis, will always be that the populations from which the samples were drawn have identical distributions. Okay, it's always an equal sign for the null. And the alternative is that not all populations have the same distribution. And as we are familiar, that these hypothesis tests can tell us if they are not all the same, but what they don't tell us is which one is different or which ones. The test statistic will be calculated with this ugly formula. So thank goodness this is one that our guru will do for us. So our guru, again, will calculate our test statistic and our p-value for that matter. The only thing that it doesn't do, and we have seen this before, is it does not provide a critical value. So we will still have to use a table to find the critical values, but it does give a p-value. So we can we have the p-value is always evaluated in the same way. It is compared to the alpha level. And if it is smaller than the alpha level, then we reject the null hypothesis. And if it is larger than the alpha level, we fail to reject. They are critical values. Okay, we reject the null hypothesis. The same thing. One-sided tests are critical values. Use all of alpha. Two-sided tests, we use alpha divided by 2. And our degrees of freedom is k minus 1. So the number of populations minus 1. So for example, a real estate agent sells single-family homes in the towns of Mouse Creek, Spring Valley, and Smyrna. Some homes for sale in these towns have the following prices in thousands of dollars. So there are 3 samples, so your degrees of freedom would be 2. There are 3 samples, minus 1 is 2. Okay, now when I created a an Excel sheet from this table, let me show you. It didn't work in our Guru. So I want to make sure you guys know how to modify these tables so that they are reading properly in our Guru. So when I copied and pasted this table and just had this table in here, so Mouse Creek was in the A column and these are all shifted to the left, and then I imported it into our Guru, what happened was it has to be a table for these types of analyses. We're no longer doing data frames. Those were in the first part of this course. And the table is two-way, meaning the rows represent something different from the columns. So the rows were the sales in thousands of dollars of the homes, while the columns were what area those houses were sold in. So you have to do a two-way table. So it automatically assumes the first column are labels and the first row are labels. So what happened when I first uploaded this data set without this column here that you're seeing is that it saw Mouse Creek as a label, and therefore the analysis was only done on two of the areas. And I was like, whoa, why is this all weird? And then that's when I realized for two-way tables, we need two-way labeling. So you have to input an extra column here, and literally I just put dumb labels on. You could just number it 1, 2, 3, 4, 5, 6. I put some labels on it. They're sales. I could put sales in thousands of dollars, whatever. But this is the first sale, second sale, and so on. So that needs to happen for our Guru to read your data set properly. Now, this is already done for you in these data sets, but in case you were trying to do something in my stat lab, I just want to make sure you know how to modify a two-way table so that it reads properly. All right, so with this example, we're going to use the Kruskal Wallis test to check whether the house prices in these samples come from identical populations, and we will set our alpha level at a 0.05. All right, so let's actually jump to our Guru right now before we run through the solution. Well, you know what? We have to do the hypotheses first. So n is equal to 16. The house prices are assigned overall ranks. In the following table, the ranks are shown in a column next to each observation. Okay, so if we were doing this out by hand, looks very similar to the rank sum test of Will Coxon that we did in the last video. But notice that you use all three samples and you merge them together to be ranked as one. That's the same thing we did for the ranked sum Will Coxon test. And then let's set our hypotheses. So the null hypothesis represents that the samples come from populations with the same distribution, and the alternative is saying that they come from different distributions. The sum of the ranks for each city are as follows. Okay, so after we have ranked each one of the samples, then we add the ranks and we get a total. So rank 1, there's 32 total for Mouse Creek, 64 for Spring Valley, and Smyrna is 40. The ranks are done the same way we've done in 11.2, where the lowest dollar amount gets rank 1, the highest dollar amount gets the highest rank, and anything that ties, you take the ranks they would have held and add them together and average them. Okay, that test statistic, don't you worry, we're going to do in our Guru. We do not have to use that formula. Yay. But we should see in our Guru that the test statistic comes out to 2.27. So let's see that happen. Let's go to our Guru together. I'm going to have to find it first. Hold on. I don't see it in there, so. Try this again. Sharing this? I don't think I'm sharing this yet. I'm not. Oh, here we go. Found it. Okay, so I'm going to log in to my RGuru account. Let me remind you how to upload data. So you're going to go to data and then data import. And we are working with a table here, so we're going to import a table. You're going to choose the file. So wherever you saved it, you're going to choose that file. I don't even know where mine is now because I've already uploaded this. Once you choose the file, what you do need to fill out after is the row and the column name, because this is a two-way table. So your rows, remember, were sales, and you could put sales in dollars or sales in thousands of dollars, however you want to label it. And your column variables were the towns. So just make sure that you label these, and you could type frequency here if you want. It's going to keep frequency there regardless. It doesn't matter. Okay, then you would hit OK, and it would populate in here. So we are using 11.3. This is the first one, not example 2. We have 2 examples in this PowerPoint. Remember, always double click on what you have uploaded here to make sure that it uploads properly. That's how I realized that one of my 3 towns were not included in the table when I did it the first time. And it should look like this for a two-way table. You see sales 1 and the 3 data values separated by towns, and you have labels up here. So always double check that the table imported properly. Then we're going to want to go to analytics, analysis, non-parametric ANOVA. Now, the only option that we cover that they actually do is the Kruskal Wallis. It is under a one-way ANOVA test, not the two-way ANOVA. So we're going to select our data set. Remember the first example of Kruskal Wallis. This response is always going to be frequency. And when you select the factor, you're selecting what you're comparing in the null and the alternative hypothesis. And we are trying to compare the towns to see if their distributions are different. So that means the factor has to be towns. So that's really important. It's typically the columns that we are focusing on in the hypotheses. So you're going to want to select that as your factor. Our alpha level is 0.05, and we're doing a Kruskal Wallis. Let's hit our eyeball. Okay, so we see that we have 18 cases, but only 16 are going to be used for analysis. Hopefully you guys are now full familiar that if the signed differences are zeros, or we have issues with them, then those aren't counted in the sample size. So we have 5 for Mouse Creek, 5 data values for Smyrna, and 6 for Spring Valley. There are no missing values. The count is 16. Okay, so I don't know where 18 comes from, actually, now that I think about it. And then we look at the test has been done here. Look, our test statistic 2.27. So it calculated the same thing that was done out by hand. And we have our p-value. So we can already make a decision right now. Our p-value is huge. Okay, really, really big. Remember, p-value says that there's a 32% the probability that the sales are due to just random chance variation is 32%, which is huge. That is a huge probability that this is just by chance, that this is not something significant. So we would fail to reject the null hypothesis. But if we were doing a traditional method or a critical values method, then what we need to do is we need to compare this chi-squared statistic to the critical value. Now, the critical values are not found in our guru because our guru gives you the p-value and it knows you can make a sound decision just using the p-value. But to find the table, now the critical values for a Kruskal Wallis is just the chi-squared distribution. So there is no special table. We'll actually use the chi-squared. So recall, I showed you guys and reviewed this, I believe, the last 2 videos, but let's do it again. When you're in my stat lab, you're going to want to go to chapter contents, scroll all the way down to the bottom to appendices, and then you have all of your tables here. So we're actually using table 6, the chi-squared distribution. So when we look at table 6, we see that we need to recognize the degrees of freedom matched with our alpha. So our alpha, and this is for a two-tailed test. Two-tailed or right-tailed. So we have 0.05 as our alpha, and our degrees of freedom, remember, are the number of samples minus 1 is how the Kruskal Wallis works. So it's not 16 minus 1, it's not 15, it's 3 samples minus 1, which is 2. So our critical value is 5.991. 5.991 is our critical value. And we're comparing that to a test statistic of 2.27. We already know they are drastically different. And we also know that chi-square distributions are primarily a right-tailed test, although this one is set up to be two-tailed. Let's head back to our PowerPoint to follow this through. So we got the proper test statistic. And we have properly identified that there are 2 degrees of freedom because for degrees of freedom, the number of samples minus 1 is used. And we have also found the correct um, critical value, 5.99. So we are failing to reject the null hypothesis on the left side and rejecting on the right side. And we very clearly fall inside the fail to reject zone with our test statistic being very, very, very much smaller than our critical value. So sorry, the conclusion would be that we are failing to reject the null hypothesis and stating that the house prices do not differ significantly in these 3 towns. Okay, our second example, a traffic safety engineer records the braking distances of a test vehicle at a fixed speed using 3 different brake pads. Braking distances in feet and their respective ranks for brake pads of type A, B, and C are given in the following table. Is there sufficient evidence at a 0.05 level to conclude that the braking distances for the 3 pads are not all the same? So here is our data, our table. We have brake pad A and the braking distances of the vehicles that were tested. Brake pad B and brake pad C. So when you open this Excel file, which is the KW Kruskal Wallis example 2, you'll notice I had to again edit this table to make it viable for our guru to read. So the ranks had to be deleted. Those columns needed to be deleted out of the data set. And we needed to input a column on this left side that had labels of braking distances in feet. We already have our rank sums for each one of these because this is being done out by hand, but we're going to do it in our guru. So let me actually show you. No, I guess I can't because I'm in presentation mode. Okay, so make sure you modify your tables properly before putting them in our guru. Remember, you can make them from scratch if you think that that's easier, and it just might be, especially for small data values like this. And you can go back to one of my previous videos to remind you on how to create tables, or our guru has a ton of videos easily accessible right in the our guru platform. So our null hypothesis is going to be set to the braking distances for the 3 pads are the same, they do not differ. And our alternative states that at least one of the braking distances is different. And in order for it to be considered different, it would be significantly different. Notice that there's no direction given. It's not stating they're looking for a braking pad to be a farther braking distance, which would make more sense that actually, no, it would be the opposite way around. We want a shorter braking distance. We want to brake and brake fast. It would make sense that we'd want to test to see if there's a braking pad that is a shorter distance. But it seems here that they're just trying to see in general if there are any that are different. Okay, the ranks of the observations are given in the table. The sum of the ranks for each type of brake pad is found in the last row of the table, and we have the rank sums here. Okay, those rank sums are used in your formula for the test statistic that luckily we do not need to mess with because we are going to use our guru for that calculation. So jumping back to our guru, again, you're going to want to go to data and you're going to want to import a table. I've already done that in my case, so I double click to make sure it imported correctly. I see that I have break pad A, B, and C for distance 1 or row 1 of the table, and the corresponding values written. Under Analytics, Analysis, go to NonParametric ANOVA, select the example 2 data set, type in frequency here. We're doing a one-way analysis, even though it's a two-way table. And remember, you always select the factor that the hypotheses are expressing. So we're not expressing distance, we are expressing difference in break pads. Alpha level is still 0.05, and we're running a Kruskal Wallis. Okay, so now we can see that we have a chi-squared statistic of 6.02 with a p-value of 0.049. Ooh, this is going to get interesting. This is one where I would highly recommend that if you weren't planning on doing a traditional method or critical values analysis, that you do one, because this p-value rounds to 0.05. So it is right on the threshold of between rejecting and failing to reject. So I'm very curious to find out what is our critical value and how close is this test statistic to that critical value. Because right now, this p-value we set to 0.05, but if we made it more specific, like a 0.01, we would have more of an answer here. Or if we set the p-value to 0.1, we'd have a completely different result. So heading over to our table, we are using a 0.05. There were 3 break pads, so we have the same degrees of freedom. So ironically, or not so ironic, we have the same test statistic at 5.991. Okay, so we have our test statistic is very close to our critical value. Let's follow this example through. So we see that our test statistic is 6.02 and our critical value 5.991. We are always looking at a right-tailed test for the most part when we're using a chi-square distribution. And because the 6.02 ever so slightly falls into the rejection zone, and we see that our p-value is ever so slightly less than 0.05, we are just about barely rejecting the null hypothesis and concluding that the break distances are sufficiently different. Okay, so that one I would, if I was a statistician or a data scientist that was trying to come up with this particular conclusion for my client, I would highly recommend that more data be collected because of how close the analysis is. I would feel uncomfortable making a strong statement one way or another, and I would then advise the team to provide more data in order to make a better analysis. So that concludes 11.3, our Kruskal Wallis test using our guru, and I'll see you guys next week.